Hi everyone, this is Srikanth and of course I know it's been a long time since I've uploaded any video or streamed anything on my channel. There was a reason for it. I changed my job and I'm not getting as much time as I used to get in the college, and the job is keeping me busy, and that's one of the reasons why I haven't been able to stream anything lately. Okay, but anyway, mm, today we are going to talk about robotics. Yeah, that's the thing we're going to study. Of course, if you are aware of robotics, there are a lot of topics and there's a lot of mathematics involved in using the robots for our advantage. And speaking of the topics, I am already aware of the DH notation, the homogeneous transformations, the composite transformation matrices, and stuff like forward and inverse kinematics. The thing which I haven't been able to study till now is the dynamics part of it, and that's what I'm going to try to learn in this today's stream, because this is just an unplanned stream, and I'm not prepared for that at all. So there are chances that I might end up making a lot of mistakes, but I just request you to be patient and hear me out. Thank you. So just to update you with what I'm doing, at the job. I'm learning a lot of different software. So when I shifted to the company, it was the first software they wanted me to learn about was the Robotics, which is a software from Creo, which is used for documentation purposes. It uses something called what was the name of that scientist, the biologist, evolution theory. We are Darwin, some kind of Darwin structure is being utilized for storage of information and updation of information in a very fast way. But that software, to me, it appears to be a little old and very difficult to use. Maybe I've not used it much, so maybe there is a lot of other advantages that I'm not aware of. But I'm going to slowly get to learn them anyway. Um, for those who don't know about that, let me just tell you, it's kind of a documentation software with multiple outputs. It gives us an output in the form of a website, which we can host it at multiple locations, or it just gives it as a PDF, or there are also options of the Kindle version, I guess. And yeah, the offline help format was also one of the options, but it seems that option has been discontinued, and almost none of the software that we use nowadays use that format anymore. So yes, so those are the two formats that we can use Robotics for. One is the PDF, and the other one is the output, the web format, and that's what we are doing. For some companies, we tend to develop those, and for some other companies, we develop the PDFs. The next software that I came in touch with was the Creo Illustrate. Yeah, that's a very powerful software, I would say, because very complex assemblies can be imported into it, and it can generate illustrations of those things for user manuals, service manuals, part catalogs, and all sort of things. And this is a very powerful tool, I would say, because it lets us do a lot of stuff, image generation, to be specific, a lot faster. So I'm learning to use that as well. And then because now you know me, I am not satisfied with any software that is given to me by the company. So the same happened with my college as well, and I continue to experiment with a lot of other software, and that actually was one of the reasons why I was able to get this current job in the first place. And I think I'm continuing to follow that trend and experimenting with other software. Like I'm trying to learn about the Blender, which is the free animation software, and plan to someday use it for creating illustrations, not only illustrations but animations, videos, and advertisements, probably in a very long run. So yeah, Blender is another software that I came in touch with. And then recently I came across a software called as Plasticity, which is appearing to be a very good 3D modeling software, especially meant for artists. So it's a CAD software but meant for artists. Blender, I would not say it's a CAD software, it's just a mesh editing software, which is very good for animation. It has uh, a lot of features that will be good for artists, animators, people who want to make 3D animations, and more creative kind of stuff, not very technical. But when it comes to plasticity, it has ability to allow us to use the same infrastructure, the same file formats, or the same, what is, I don't really know what to say about this. So maybe the core or something. The Parasolid infrastructure, I guess, is something that is used by this. And Parasolid is used most of the CAD software, allowing technicians to do edits, to build 3D models and make them very fast and very accurately using the dimensional data. But these were very difficult to be used for the animators and artists, because it becomes too technical at one point, and artists don't really want to be associated with a lot of dimensions, because they have to continuously edit their models and be creative in the process, and that's what makes the CAD models very difficult to use for the artists. But this software, Plasticity, as it uses the CAD infrastructure, the Parasolid uh, at its core, and so all the editings that we are aware of in the CAD software, like moving a face or in methods, other edits, this is available in the Plasticity software. And at the top of that, we can just export mesh of these 3D models that we generate to work it in any of the 3D modeling and animation software. And this was earlier very difficult, because to get the mesh properly working in a mesh format, it's slightly difficult. A lot of people have felt that pain, and I guess a lot of people continue to feel that pain. And this came as a real, really surprising thing. But of course, I wasn't able to convince my management yet to purchase the software, because the software is relatively new and a lot of features are supposed to be added into it in order to make it more reliable and user friendly. It already is a very user friendly software, but I think what it lacks is reliability, because a lot of times it doesn't tell us what it is exactly doing, and gives us the output a lot earlier than it is ready for importing or exporting to work with. And that sort of makes it unreliable, because we don't know what kind of machine, how many parts are actually imported and exported, and that can become a real headache when you're working with technical illustrations. Anyway, but that is definitely a software which I will always keep in my mind if I really want to work on it in future. So, having done away with whatever I've been learning in my job, let's come back to what we have here today. So today I want to focus my attention on learning something about robotics, something that I have been wanting to learn for a long time, something which now uh, is also an extension of the basic fundamental thing that I've is not pretty much understanding the other subjects as well, like when it comes to finite element analysis, the dynamic modeling in that, and even the dynamics of machines. I was able to handle that subject pretty well compared to the other software, but still there is a lot that I have to learn when it comes to dynamics. And today I'm going ahead and trying to learn the dynamics part, because I'm going to try to do it using the ChatGPT version. Let me see if it is able to get me to learn all the few things on that. I did try to use it earlier as well, try to ask it how to generate a few things, but it gave me data that was not in agreement with the textbooks. I wasn't even able to verify whether it is giving me the right data or not. I don't know, probably it should be going somewhere placed. Right, so coming back to that particular thing, I guess I think I have an image right here. Okay, so this okay, come on. Yeah, this is the assignment that I was supposed to do for a student, but I wasn't able to do because I didn't have an idea about the dynamic equations and all. I guess Jacobian is the way to go for that, because unless we are able to find and use the Jacobian, we won't be able to do any even inverse kinematics or the joint space, those Cartesian spaces, stuff like that. These kind of conversions can only be done using the Jacobian matrix, and finding the Jacobian could be very critical to this. But anyway, when it comes to the dynamics part, there is one thing that I've always heard about that is Lagrangian something. What concepts are necessary to be able to compute the dynamic analysis problems in robotics? Let's ask ChatGPT if it is able to correctly answer this particular question. First, I would just ask it what concepts are necessary to understand the dynamic analysis problems. Of course, the syllabus that we are teaching here in college, it is really old, and a lot more stuff could have come up in the recent time that is driving the robotics technology to much ahead of what we're teaching in the college. But let us see if you're able to connect to this. So a few things that it has presented, I'm aware of it. Let's see. The dynamic analysis of the robots, it involves understanding and modeling the forces, torques, active robotic joints, and length-sized nodes. To tackle the dynamic analysis problem in robotics, you need strong foundation in several concepts. Of course, kinematics is something I'm very well aware of, and I don't think I'll need much on this. Neural mechanics, been teaching it for about more than 10 years. So again, I don't think it's going to be necessary for me to understand that. So this is where the problem actually starts for me, I guess, where we have the Lagrangian mechanics. I've not heard these two words used in combination till now, but let's say that the mathematics used in Lagrange is implemented in mechanics, and that's what it is calling it as the Lagrangian mechanics. So this advanced topic provides a powerful framework for deriving the equation of motions for complex robot systems. The Lagrangian formulation helps translate the robot's motion into differential equations. Okay, so then we have the Euler-Lagrange equations, and these are fundamental in deriving the robot's equation of motion from the Lagrangian. So first, we probably have to understand the Lagrangian, and this is probably a continuation of the Lagrangian equations. And then we have the dynamic equations. We need to derive and solve the dynamic equations that describe the relationship between the joint accelerations, joint torques, and external forces. These equations are usually in the form of second-order differential equations. Okay, so two constants to be solved. So a lot of input is going to be required here. Then we have the mass distribution and inertia. Understanding how mass is distributed along the robot's links is critical for accurate dynamic analysis. We first have the center of mass, center of gravity for that to take care of. Then we have the moment of inertia. Of course, this is going to be important because the amount of torque which will be required in case a lot of angular acceleration is involved. There, the moment of inertia will play a very critical role in finding out how much inertial torque will be resulting on the robotic joints. Okay, anyway, so with respect to rotation, translation, so these are essential concepts. Okay, the joint types and actuators, then multi-body dynamics, then the control theory. Control theory is broader than just dynamics. It is essential for implementing control strategies that take into account the dynamics of the robot. This involves feedback control, PID controllers, and more advanced control methods. This is more inclined towards the electronics thing, so I'm probably not very comfortable taking up this part. Anyway, so next we have numerical methods. Dynamic analysis problems involves solving complex system of differential equations. Proficiency in numerical methods for solving these equations is vital. Okay, so in cases where we won't be able to solve the differential equations by using the traditional analytical methods, we'd probably have to go around and use the numerical methods, which are more not the kind of approximation methods. Result might not be exactly what we actually want, but it's got to be sufficiently close to what we need in engineering. Then we have matrix algebra and linear algebra. Okay, so I'm good with matrices. No problem. Linear algebra is also my stuff, so not a big deal. Computer programming, Python and MATLAB, of course. MATLAB and Python make these things a lot more simpler. But I don't have the advantage of using the MATLAB for now because I don't have the license of MATLAB. I did have an online MATLAB educational version for some time, but I don't think it is any longer available to me. Then we have the mathematics of this, mechanics, design, right? So most of these things are known to me. So the best part I think I should start with is the Lagrangian mechanics. So let's try to understand Lagrangian. Explain to me what is Lagrangian. Okay. Let's see if you're able to understand this. It's going to be complex, of course, but I'll try to understand it at least. The Lagrangian is a concept from classical mechanics that plays a crucial role in describing motion of physical systems and deriving the equation of motion. It's named after the Italian-French mathematician and physicist Joseph Louis Lagrange, who introduced it in the 18th century when I'm not interested in history a lot. At its core, the Lagrangian is a scalar function that summarizes the inertia-related properties of a physical system. It's defined as the difference between the system's kinetic energy and the potential energy. Okay, so the difference in kinetic energy and potential energy is something that is stored. Yeah, so we have a simple equation, L equals T minus U. L is the Lagrangian of the system. T is the kinetic energy of the system, which depends on the velocities of the system's components. And U is the potential energy of the system, which depends on the positions of the system's components. So this potential energy is going to be the motor energy is going to be an external thing, a force kind of thing. So I don't think it's going to be potential energy, so to say. But gravity is going to be one potential energy that will definitely add on it. And if there are some springs used over there, that too can be considered as potential energy. But springs and gravity are not going to play a major role here when we are doing the robotic dynamics, so it's probably kind of something else. So we'll have to just check it out if the motor energy, the electric energy that is used to convert or provide the torque in the robotic motions, if that can be considered as a potential energy. No, at this point I just have to go with the flow. Let's try to understand what is there. So the Lagrangea provides a way to express the system's dynamics in terms of generalized coordinates, just set of independent variables that describe the configuration of the system. Complex words. Let's start understanding the, for example, in the context of a simple pendulum. The generalized coordinates could be the angle that the pendulum makes with the vertical. So we don't really have to worry about the x and y coordinates with respect to the Cartesian plane. we just have to take care of the angle of the pendulum that it is moving on with. Because the motion is going to be coplanar, and all those oscillations are going to be happening in the single plane, and the thread link is not going to change. We can just worry about the angle that the pendulum makes, and that's to take care of everything else that we need to speak about. All right, so using the Lagrangea, the equations of motion for a mechanical system can be derived using Euler-Lagrange equations. Oh my god, so Euler-Lagrange equations, what these are. So this is where a lot of calculus is coming up, and this is what actually terrified me to start with. Here I am trying to understand this again. So let's understand what are the notations used here. So Q is the generalized coordinate. Okay, so in case of a single pendulum, because the angle, and so whatever is the defining minimum parameter required to define the position of the robot, I guess that is the generalized coordinate. And then the Q dot is the derivative. Yeah, dot usually is the derivative. So derivative of the generalized coordinates with respect to time. Okay, so if theta, if in case of the simple pendulum, if you take theta as the angle made by the pendulum with the vertical, then d theta by dt is going to be q dot. So what's L? Yes, L is the Lagrangian that we studied earlier, right? So both the potential and kinetic energies need to be expressed in terms of theta, which is the generalized coordinate for this for simple pendulum. And then we have to differentiate with respect to q and q dot. Q being the general coordinate, so dl by d theta and dl by d theta dot. Is it dou q is q dot? Is it q dot is dou square q? Well, something. Yeah, see, this is where it just goes out of my understanding. Okay, so Q is the generalized forces actual system. Euler-Lagrange equations essentially describe how the systems Lagrangian changes with respect to time in generalized coordinate systems. Yeah, a lot of theory, but I'm interested in application of this particular thing, so let's ask if it is able to explain the Lagrangian formulation of a simple pendulum. Explain me the Lagrangian formulation of a simple pendulum. All right, let's see if you will understand the question and do it. Lagrangian formulation can be applied to the analysis from pendulum, which is a mass pendulum arm attached to the spring rod of fixed length. The goal is to derive the equation of motion of the pendulum using the Lagrangian approach. Okay, in this case, let's use the following variables. Theta is the angle that the pendulum makes with the vertical. This is the generalized coordinates. Yeah, this one I was able to understand it perfectly. L is the length of the pendulum's string, M is the mass of the pendulum bob, and G, of course, is the acceleration due to gravity. That's 9.8 meters per second square, which is what we are using, but it could vary from equator to the North Pole. Very negligible value, so let's go. Let's stop worrying about that. So we have the step 1, kinetic energy and potential energy. So we have to find the equation of these two, I guess. So kinetic energy of the pendulum arm is given by its rotational motion of what? Length of the pendulum's string. All right, so ml square basically is the moment of inertia. So, and the theta dot is of course the angular velocity. So it's basically the kinetic inertia half I omega square. It's been written in this format. Okay. So theta dot is the time derivative of the theta representing the angular velocity. The potential energy of the ball is due to the height over the lowest point, and the height over the lowest point, is L. And the height over the lowest point is going to be L. Yeah, that's L minus L cos theta. And that difference we need to multiply it to mg, which gives us the potential inertia. So now writing down the Lagrangea, we will get it as the difference of the two equations. The kinetic energy minus potential energy, that is understood. And we have the Euler-Lagrange equation. Euler-Lagrange equations. So to derive the equation of motion using Lagrangian, we need to apply the Euler-Lagrange equations. Okay, so this is where it had told us this is where it was not able to understand completely. Let's see what we need to do from here. So we need to differentiate partially. Okay, so differentiate the Lagrangian with respect to partially differentiate is what it wants to do. So this is theta dot already, and we are differentiating L with respect to theta dot. Oh, so we are interested in finding this value first. So we are finding that over here. So when you differentiate it partially with respect to theta dot, the differentiation of this entire term is going to get 0. Wait. We are differentiating this term with respect to theta dot. So yeah, that's going to become 2 times theta dot, and 2.5 are going to cancel, and we just left this particular value. That's okay. When it is trying to differentiate the other term with it, we are interested in theta dot. We don't have any theta dot in here, but theta is basically used to derive theta dot. Because this is partial differentiation, probably that's not going to work in here. And then we have to partially differentiate the equation with respect to theta. When we do that, 1 of course is going to become 0. Then we have differentiation of minus cos theta, it becomes sin of theta. So this and these are the two equations we obtained. Substitute it back in here. Okay, so we get d by dt of this particular equation, and then we have this particular equation. So when we simplify the derivative, right, so these two are constants, it will not be affected. So we're differentiating with respect to time. Theta dot is already differentiated with respect to time. We have double differentiation of theta here, and this term remains as it is. And then because the other side is 0, we can just take whatever is common in these two and send it to the other side. Okay, that's what basically we're getting is the same equation that we get in dynamics, simple harmonic motion, right? T dot will dot. Is it similar? Actually, I don't know. So this is the equation of motion for the simple pendulum in terms of angular acceleration and the theta. Okay, it's a second-order nonlinear differential equation that describes how the angle of the pendulum changes over time due to gravity. This example demonstrates how the Lagrangea approach can be used to derive the equations of motion for a simple pendulum, providing a concise and elegant way to analyze its behavior. I'm not really sure what's going on here. What is this equation? So we have the acceleration part, the angular acceleration over here, we have the angular displacement over here, we have the length over here, and we have the acceleration to gravity. So for a given pendulum, these values remain a constant, and for what did we know? The value of angular acceleration, we'll be able to find the position at which it's located, or provided we know the location, we'll be able to find what is the angular acceleration of it at this particular point. Good enough, but a lot of problems can be also made in this analysis. Okay, let's Lagrangian for now of our robot in 2 dimensions, let's say. Analyzing motion of robot. This is going to be used transparent. Let's see if it is able to give me the correct answer. Certainly, let's go through the step-by-step derivation of Lagrangian for 2D RR robot, which is privileged choice. Then I'll explain how the Lagrangian can be used for analyzing the dynamic motion of the robot. Fine. So first, define the variables in kinematics. Consider a 2D RR robot with 2 privileged joints. A robot has 2 links, length L1 and L2. The joint angles are theta1 and theta2. And effective position can be represented by x, y. Use the forward kinematics equation to relate the joint angles theta1 and theta2 to the end effective position x and y. And step 3, calculate kinetic energy and potential energy. Now the way to do that is to use half mv square. So you're finding the velocities at the end point of this, or is it the center of gravity? So v1 and v2 are the linear velocities of link L1 and L2. And he says link L1 and L2, what is it going to mean? It's probably going to mean the velocities of the center of gravity itself. So for a point mass m with linear velocity v, the kinetic energy is given by half mv square. Okay, then the potential energy u